taking some time here today and joining on our webinar. My name is Gary Osman. I'm the applications engineer for Swagelok Pittsburgh tri-state area, and I'll be the host here today. We have a wonderful webinar on Swagelok Regulators, Selection and Optimization. Our presenter today is Jon Kestner. He's the field engineering supervisor with Swagelok Company. So let me get into a little bit of just housekeeping items here. Try to keep your microphone muted throughout the presentation. We might have a break or two to pop in and let people interject a couple questions that are here, but primarily let's try to utilize that chat function. So it's right there on that little hovering toolbar on the bottom third of your screen there, icon to pop up the chat. I'll be monitoring that and interject when appropriate, or kind of when we have breaks to do some Q&A sessions. So utilize that as much as possible. Comment, question, whatever you feel you want to talk about, go right ahead. You can leave your cameras off. There's really no need for that. You'll be able to see me when I'm talking and Jon when he's presenting. So that's how we'll utilize that. And outside of that, any questions or concerns after the session can be directed at your known, sales rep that you're already in contact with, or myself. My contact information is there and will be posted again at the end of the presentation. So we're going to get this thing kicked off. Hopefully everyone can be pretty engaged, ask some questions, and we'll pick up a couple things that we didn't know before the presentation started. So with that being said, I will turn it over to Jon, and we'll begin the presentation.
Great. Thanks, Gary. So as Gary mentioned, my name is Jon Kestner, and I'm currently the America's Field Engineering Supervisor. So I take care of northern half of the U.S. and then all of Canada. And within the Americas group, we have nearly 60 field engineers. So folks like Gary, who operate in a specific territory. And we've got, like I said, about 60 field engineers throughout the Americas. And then globally, we have almost 150. So we've got a really wide-ranging team with a ton of different experiences. And actually, prior to this role, I was the regulator product manager for Swagelok. So as soon as Gary asked if I'd be up for giving a talk on regulators, of course, I said yes. It's something I spent about 5 years working with the regulator product line, and then prior to that was actually a field engineer myself, and dealt a lot with in the field regulator troubleshooting, sizing, selecting, things like that. So so don't hesitate. I'll reiterate what Gary had said. Don't hesitate to ask any questions that you might have in the chat. I'm happy to answer just about as off the wall of a question as you could ask, right? Having been around regulators for some time now, I can't say I've seen it all, but I'm always excited to see what new types of applications or challenges are out there. So feel free to ask away. So today, what I want to do is cover aspects and the behavior of pressure regulators, and do that in the context of regulator selection. So we're going to start with a little bit of regulator theory, so just what makes a regulator work, and then get into the selection process that that I use when I'm thinking about selecting a regulator, and what we've kind of rolled out as best practices for regulator selection. And in each one of those steps, we're going to talk about different regulator concepts and how they relate to what that choice does for the regulator. So as we go through that, we'll talk about the functions, things like creep, lockup, droop, supply pressure effect, if you're familiar with any of those terms. If not, don't worry about it. You will be familiar by the end of this talk. So with that, I always like starting with this kind of cartoon, right? And what it does is it contextualizes where regulators are used in their different types. So there's two main types of regulators. One is pressure reducing, and the other is back pressure. So pressure reducing regulators do just what their name implies, right? They take a high pressure source, whether it's a gas or a liquid, they take a high pressure source, they reduce that pressure down to something that's usable for a process. And that process can be a whole host of things, right? It could be a lab test bench, it could be a continuous chemical process, it could be, tank filling, whatever it is, right? It can be anything. And then on the other side there, you have back pressure regulators. And so where pressure reducing regulators drop pressure and they want to control the outlet or what's downstream of the regulator, kind of pressure reducing regulators look forward. Back pressure regulators, as the name implies, they look behind them. So back pressure regulators are controlling the upstream pressure, and they're keeping that pressure within a specified limit, right? So you can use back pressure regulators to relieve excess pressure, things like that. Almost think of them as a very sensitive relief valve, right? Obviously, they don't slam open and dump a bunch of pressure, but they operate in a similar way. Now, most regulators used in the industry are the pressure reducing type. We see about 75% pressure reducing to 25% back pressure. So most of our discussions today are going to be around the pressure reducing type of regulators because those are most common. A lot of the concepts we talk about are applicable to back pressure regulators. And if you do have back pressure regulator questions, don't hesitate to ask. We just won't cover a ton of that content today, but I'm sure Gary and the team would be happy to have further discussions, or even a quick session on what those back pressure regulators can do, if there is the need for that. So again, don't hesitate to ask back pressure regulator questions. So when you think about a pressure reducing regulator, this is a pretty typical cutaway of a general industrial spring-loaded pressure regulator. So this is a Swagelok KPR, but it's representative of most regulators you'll see in industry. So what you really have with a pressure reducing regulator is two zones. You have your high pressure inlet and a low pressure outlet. And that low pressure outlet is really what we care about, right? That's why we're using a regulator, is to get that low pressure. And the switch, or the barrier between those two, is what we call is at the control element. So there's a poppet and a seat, right? That move, the poppet either moves further away or closer to the seat to create that pressure drop that's required for whatever process we're using the gas or liquid for. Now, we as regulator users need some way to tell that regulator what to do. And we do that through the loading element, right? And so most often this is a spring. We'll talk briefly about dome loaded regulators here in just a bit, but the loading element, in this case, you turn the handle, compresses this spring, and that allows the user to dictate what that outlet pressure is. And now it's not good enough. You can't just turn the spring and expect the poppet to move on its own. You need some way for those two elements, the control element and the loading element, to communicate, right? And that's really the job of the sensing mechanism. So typically a diaphragm or a piston. And the loading element then applies a force to the sensing element, which in turn contacts your control element and tells it, hey, you need to open up more, or get closer to the seat, and allows the regulator to deliver that low pressure that you want. And so these three elements, the control element, the loading element, and the sensing element or mechanism, really drive pressure regulator performance. And so you'll hear me talk about them a lot today. And the way that they operate is in a balance of forces. So there's four forces that we care about within a pressure regulator. One is the loading force. So we talked a little bit about that just now, right? When we compress the spring or allow that spring to relax, that loading force is going to change. Next is the inlet spring force. So most every regulator will have some sort of spring that keeps the poppet pushed against the seat if there's low or no inlet pressure to help do that. And that's a really light spring, but it is something we have to consider. Next is the outlet pressure force. So this is what we care about, right? So that's all the force that's created by the outlet pressure acting on the underside of that sensing mechanism. And then finally is the inlet pressure force. So while the area is smaller on the poppet, there is some force that's created by that inlet pressure. And that does play into the balance of forces. So you could probably tell what the equation might look like just based on the arrows, but the F1, our loading force, has to balance out against F2, F3, and F4. And the regulator is going to constantly self-adjust to maintain that balance as best it can. And so you'll hear me talk about this quite a bit through the next sections. So I wanted to be sure we had a baseline of just what's going on in these regulators. So if we turn the handle clockwise, right? So we're compressing that spring. The F1 goes up, right? We've compressed the spring, increases the force. And the only other thing, if we assume that our inlet pressure or our inlet source is large enough that it's not going to change by any appreciable amount. So F4 is the same. The inlet spring force, that doesn't change a lot, right? It's kind of just a light spring. So the only thing that can change to maintain that balance within the regulator is F3. So F3 has to also rise by some proportional amount, right? And that has everything to do with the sensing area and all that. We'll talk about that in just a bit. But that's really how the regulators operate, is when any of those inputs change, the balance of forces inside the regulator works to equalize itself. So when we're thinking about regulator selection, we will continuously come back to the balance of forces. And I view selecting a regulator really as a 7-step process. But in reality, steps 2, 3, and 4 are where a large amount of the regulator specific work comes in, right? So inlet pressure, pressure control, and flow requirements. So we'll spend a lot of time talking about those 3 sections, and the others, they are important, but they're also similar to any time you would select a valve, right? Or even a fitting, right? You need to know that the compatibility is there and things like that. So so we will go through 7 steps, with majority of the discussion happening in steps 2, 3, and 4. So first and foremost, we need to ensure that the function of the regulator is what our system needs. Now, I've just got an overview of some of the regulator types. There are many out there, for especially as you get into very specific applications, vacuum regulators, steam regulators, things like that. The 2 big ones obviously are pressure reducing and back pressure that we talked about. And back pressures can really be set up in 2 main configurations. One is kind of teed off of the main line, and that's typically where they're being used to limit the upper end of the pressure, right? So the back pressure regulator is a very sensitive and repeatable way to open and close and shave off some of that excess pressure if you do have fluctuations, or you can use it in line, and that really maintains an upstream pressure. So we see this a lot in like the backside of liquid analyzers in an analytical space, right? If you need to keep that analyzer at a certain pressure, back pressure regulator will be great. Differential pressure regulators are when you want to reference a other part of the system or a different system, and you always want the set point to track along with a little bit of differential on top. Changeovers do exactly what the name implies, so they automatically change from one source of gas to another, and that's to ensure that you have constant pressure delivery. And then vaporizing regulators have a heating element in them to help the vaporization process. But again, you can get into many different types of these specialty regulators. This is really just a few examples that are very common. So once we figured out the function of the regulator, the first thing is to ensure that the inlet pressure range matches what we expect the system to deliver. And that's going to affect really two elements in the control element, or two components, I should say, in the control element, which will drive some of the regulator's behavior. And so that is the seat choice, right? So low pressure applications can really use more elastomers than a high pressure, which might require a harder kind of harder plastic material, PCTFE or PEEK, something like that. And then also the poppet spring. So I mentioned that before. That will change based on the inlet pressure, although it has less influence in the regulator's behavior. So the first behavioral impact that the seat choice and ultimately the inlet pressure plays is lockup. So lockup is the change in pressure. It's this tail right here that the regulators experience when the system goes from flowing to not flowing, or not flowing to flowing. So it's the start and stop pressure difference that you see. And that has everything to do with the regulator seat creating a full seal. So you can imagine when the regulator is shutting off, there's a point where you're almost not flowing and the poppet is touching the seat, right? But it's not quite shut off yet, because you need to push that poppet into the seat, create a little bit of deformation, and that will create your full seal. Now, that little bit of deformation takes some force, which in turn relates to the pressure you see on the outlet. Now, on the other way, you have to give all that back in order to start flowing. So if you have to unload the seat, that's where you see this sharp drop in pressure. And so lockup really operates both ways, right? I think folks generally think of it as when the regulator shuts, but there's also a drop when you begin flowing again. And so, so the seat material choice does have a impact on the amount of lockup, right? So lockup is dependent on the poppet spring force, obviously, and the inlet pressure force, which is driven by the inlet pressure, right? And so the force needed to compress a O-ring versus a hard plastic seat can be very different, right? And while it's not always possible, right, to lower your inlet pressure, if you do have a lower inlet pressure, you will see less lockup. But even if the inlet pressure stays the same, choosing a model which most closely matches that inlet pressure will ensure that you're not using a seat that's over-spec'd and might require more force than you would expect to fully shut off, right? So, using the elastomer seats where possible will help lower lockup. Now, another aspect of regulator behavior, or I guess some of the regulator issues you can see, is creep. And this is the most common issue I've seen in the field. And creep is the rise in outlet pressure when there's no flow. So essentially a seat leak, right? And creep is typically caused by some sort of debris or damage on the seat. And we see, these are two pictures of regulators that had been returned to us, and they represent very typical debris that we see in regulator seats. And there's really two types, right? The one here on the right is looks a lot like a tubing burr or something like that. We see that quite frequently on system startups, right? You can imagine whole system is built and maybe there's a pesky little burr still sitting in there. Now as it zips down the line, the space between the seat and the poppet is very small to create those pressure drops. So that burr is moving pretty fast and it's going to embed itself in that seat, right? Causing a small leak path that is between the poppet and the seat. And even if you get some extra closing force, and maybe you have a higher inlet pressure, you still might not be able to fully seal and you'll see creep. Now, in the bottom left, you have a situation that typically develops over time, right? A bunch of debris is impacting the seat and embedding itself, creating all these little tiny leak paths that eventually, once there's kind of a critical mass, you end up with a seat leak because the seat can't deform around that. So the reason why we worry about creep is protection of all the downstream components, right? So if you imagine this is a test bench and the testing is over, right? So we shut off the shut-off valve, but we have creep in this regulator, right? So we have a high pressure cylinder kind of thing, and there's seat creep in this regulator. Eventually, over time, or sometimes very quickly, but over time, this downstream section could creep up from 100 psi to 120 to 170 to 250, up and up and up, and eventually damage these gauges or whatever piece of equipment we have here. Here it's a flow meter, but it really could cause some problems in the system. So we want to avoid that if we can, and there are some things that we can do to avoid creep. And one of them is to include some filters. Always a good idea. Regulators really like clean system media because they can be sensitive to that debris. Next is adding relief valves. So just downstream of the regulator, it's always a best practice to add a relief valve so you're protecting that system. And we see many people doing this, right? So it's very common. It's absolutely required in some instances too. And then where possible, shut off upstream of the regulator. It's not always possible, but where you can, that takes all of the shutoff burden away from the regulator. So regulators are not shutoff devices. They will shut off, but they're designed with pressure control in mind, not pressure shutoff or isolation. And really the biggest distinction there is that unlike something like a needle valve, where if you need more closing force, you can turn that handle and even get some tools out if you want to and really wrench down on that seat if you absolutely need to make a seal. You don't have that luxury with a pressure regulator, right? So you need to rely on that poppet spring and your inlet pressure force to shut off the regulator, and that's all you get. There is no additional closing force to be added. So if you can, take that burden off of the regulator and shut off upstream. So when selecting an inlet pressure, again, always match it to the expected supply pressure. Those softer seats, if you can use them. So this is a table from our RHPS, our process-oriented regulator series. And you'll notice that some higher pressures, you have to use a hard seat, right? Just because of the forces involved, you need to. But where possible, you will see better performance from that soft seat. So you'll see better lockup, they'll manage creep better. And so it's always good where you can to use a soft seat if those types of things are a concern. So next is the pressure control range. And so this is an important one, especially when we think about accuracy, right? And whoops, one too many. And so this is really pressure control range is really affecting the loading element and the sensing element, right? And we'll talk a little bit about both of those through this section. So first is the sensing element. So there are two main types: diaphragm style sensing elements and piston style sensing elements. And they're designed for two different uses. Diaphragm sensing elements are very sensitive, so they can react very quickly to any changes in flow, in pressures, and they're really accurate, right? Because it doesn't take a lot to move those thin diaphragms, which is great, especially at low pressures, because they can't handle the very high pressures that something like a piston could, right? Now, for pistons, some of them can have pretty decent sensitivity, but because we're talking about such high pressures, almost always you will have lower sensitivity with a piston than a diaphragm, and you'll have a slower response to any changes. Now, in some cases, that can actually be a good thing. So if you have a system that has a tendency to have pulsations in there, piston style regulators can actually help. So they can slow that system down. They won't eliminate them, but they can help, and they will certainly hold up to those pulsations a lot better than a diaphragm would. And then of course you can go up to very high pressures, right? Even greater than 10,000 psi with a piston style, because you do have that ability to machine in the large amount of material to hold that pressure. So almost more important than the sensing element choice, which sometimes is driven just by the outlet pressure you want, is selecting a range that's matched to the maximum supply pressure you might want, because that drives the spring that's used in the regulator. So I'm going to run through a couple slides kind of forwards and backwards, and I want everyone to watch what happens as we increase the flow in our sort of imaginary system here, right? So we start at about 2 standard cubic feet per minute, outlet pressure, a hair over 15 psi. As we increase the flow, watch what happens to the control, sensing, and loading elements. So we're going to increase the flow, and of course, the poppet has to open up. So we'll decrease it again here. So the poppet has to open up, which in turn allows that spring to slightly relax, right? And so when that spring is allowed to relax, then the force that it gives also goes down, right? So when more flow is needed, that F1 actually goes down slightly. And just like we saw earlier, if that F1 goes down, something else has to change. And we're going to assume that our inlet pressure isn't fluctuating wildly, or it's a big enough source where the flow is not depleting it faster. The poppet spring isn't really changing all that much, although it will change slightly, but you will have some reaction from that F3, which is the droop. So if you've heard that term droop before, that's what folks are talking about, is the change in outlet pressure as you increase or decrease flow. But mostly it's the thought of how much is my outlet pressure going to decline if I increase the flow by a certain amount. And now that is directly related to how much does my F1 change as my poppet moves. So you can imagine that a spring that can control 0 to 200 psi is much stiffer, has a higher spring rate than a spring that can control 0 to 100. And so the 0 to 100 spring range will actually show better droop performance. It'll be more accurate than the 0 to 200. Very often we see regulators selected to mimic the gauges that are used with them, right? So if there's a system that has a 90 psi outlet pressure, you may be using a 0 to 200 gauge, which makes sense. Gauges work the best in the middle of their range, kind of that middle third. With pressure regulators, you actually can select and should select that lower pressure range. So pressure regulators are quite happy to work at the upper end of their control range, and you will see better droop performance, better set point resolution, right? So every turn of the handle is actually going to give you less change in pressure, so you can more accurately dial in what's needed. And so that's a disconnect that we always try to bridge, is that, using that 0 to 100 psi regulator for a 90 psi output feels like you're kind of on the edge, but in reality, the regulator is quite happy to work there. So you'll actually see better droop performance. Now, we talked a lot about springs and how they drive kind of misbehavior of regulators, right? There is also an option to just get rid of the springs altogether. So dome-loaded regulators swap the spring force, creating F1, for a pressurized dome of gas, creating F1. Everything else in a dome-loaded versus spring-loaded regulator is the same, except for we don't have to deal with the spring rates and changing forces as the poppet moves, right? And the advantage of a dome-loaded regulator is you can see in the flow curves here, these are the same regulator, just different loading mechanisms. The advantage of a dome-loaded regulator is that you can have a much flatter or lower droop flow performance across a very wide range of flows. So we see these a lot in process-oriented applications where you might have a constantly changing flow rate or a wide flow range. That you can think of something like a supply regulator that's delivering gases to an entire laboratory, right? As those benches or hoods or whatever use different amounts of gas, the flow demand is going to change. So that supply regulator would be very well chosen as a dome-loaded regulator because your delivery pressure will be very constant. So there is an option to get away from springs if needed. But when you are selecting a control range, always feel inclined to choose the one that is closest to your maximum control pressure. And that will help not only to drive the right spring, but it could unlock different sensing mechanism options, right? So where possible, if you need that sensitivity, diaphragm sensing elements are great for that. You may need to use a piston if you have a higher pressure. And then we talked a little bit about spring rates and dome loader regulators just now. So the pressure control range is a critical piece of getting an accurate pressure regulator with good set point resolution. So now the fourth one of these sections that I said we were going to spend some time on is flow requirements. So this is another huge discussion when you're selecting a regulator, is what CV do I need, or how big of a regulator do I need, what size, right? And what I always tell folks is that bigger is not always better with regulators. In fact, it almost never is, and for a couple reasons that we'll talk about here in just a bit. But what you want to do is utilize the flow curves that are available in all technical documentation. For Swagelok regulators, we have a technical bulletin that's I think at this point a couple hundred pages of flow curves and flow information, and you can learn a lot from these flow curves as far as what you should expect from the regulator when it's in service. So I'll walk through a couple examples here of just how we would use a flow curve, right? So one of them is answering the question, can I use this regulator, right? So I have a regulator that I want to use for a specific application. Will it work, right? So let's take this pretty simple application, right? 1,000 PSI in, 175 PSI out, a flow rate of 25 SCFM, and nitrogen is our media, right? So the first thing we want to do is find the right inlet pressure. right? So the inlet pressures typically will be denoted on the legend and will be shown as either letters, numbers. Sometimes they're actually just written right on here, but in this case we have letters. So we want to find the L curves. So there's one black one in the middle here, and then there's one here, and then one here down at the bottom. And so we only want to focus on these curves because that's our inlet pressure, right? So we find the right curve, and then we find the flow rate that we have, 25 SCFM, and we start drawing it up through the L curves. So the first one is, that's not enough, right? Because we need 175 PSI. So we keep going up to find the next L curve, right? So this one, we find the intersection, we look at the outlet pressure over here. So at our flow rate, with the inlet pressure we have, we can get, oh, perfect, at least 175 PSI. So we know that this regulator, so the 1000 PSI in, and this is a 0 to 250 PSI out regulator, will work just fine for this application. So really anything above this green area in the L curve, we could even use it up to 40 or 50 SCFM, right? And we could still get some flow out of it. So that's one way to use them. Can I use this regulator? Now, the next way to use it is how much pressure is going to change, right? When I go from 0 to my target flow rate, which in this case is 150 normal cubic meters per hour. So the first thing is, again, we need to find the right flow curve. So that's everything to do with the inlet pressure. So in this case, we have a inlet pressure of just over 500 PSI. So we can find the 507 line, right? So here are the curves we want to work with. Then we want to find where we're starting. So in this case, we are starting at 250 PSI. So that is the set point at 0 flow. We set it on a bench, everything's deadheaded, 250 PSI. Then next, we want to find our target flow rate, right? So 150 normal cubic meters per hour, which is just under 100 SCFM. So we find that, we find the intersection of those two, and work our way back over to the outlet pressure. And then from there, it's just what is the difference, right, between where we started and where we ended. In this case, maybe 25 or 30 PSI would be different. And so that's where we can decide, is that acceptable for the application that we're running, or do we need to go with a more accurate pressure regulator, something like a dome load or something like that, right? So that's really what you can get out of flow curves, is the ability to better understand what to expect out of a pressure regulator. And those are the two main ways we see flow curves used. If you do need sizing help, or you want to talk through the selection, never hesitate to reach out to Gary or the local folks there. My work with the field engineers, we do a ton of regulator sizing and selection work, and really understanding what to expect. So we're always willing to help in that regard. So you can also use, for larger regulators, we see calculations being used. And, typically, and I can say this for Swagelok, but I'm sure other manufacturers do it the same way, where those calculations will most often put you in the kind of 1/3 to 1/2 the way down the flow capacity, so that you're in a good part of the flow curve. What it doesn't tell you, though, is droop. So how much droop could you expect from a pressure regulator? And one of the drivers for us to create what we've called the flow curve generator was exactly that, is that you have all of these different applications and all of these different regulators, that it's impossible to do tests to create flow curves for all of them. And when you calculate, you get a limited set of information. So what the team has done is actually created a flow curve generator that's available on .com, Swagelok.com. It's under the tools. You'll find it there. and that will actually generate a flow curve specific for your regulator you want to use and your application. And you can actually compare a couple different parameter sets, and then it also includes this velocity intercept line for those process-related applications where gas velocity is very important. So a great tool to use, and again, don't hesitate to reach out to the local folks there if you want someone to walk you through it. So I mentioned that bigger is not always better, right? And the supply pressure effect is one of the main reasons why that is. So the supply pressure effect is the change in outlet pressure when our inlet pressure changes. So this is really common in things like gas cylinders, right? As you use gas from that bottle, the pressure is going to drain and drain and drain and drain, causing that inlet pressure to go down. Now that's going to affect the outlet pressure. And in order to understand how that affects the outlet pressure, we need to look at the balance of forces. So I mentioned before, we've got 4 forces. We'll let them fly in here. F1 and F2 don't change. So we're assuming that we're not changing, we're not turning the handle at all, right? This is only the inlet pressure that's changing. So as that inlet pressure drops, our F4 goes down. Remember, that's F4 is the force created when the inlet pressure acts on the poppet. So as that F4 decreases, F3 must increase. So F4 is going down, F3 must increase by some amount in order to maintain that balance. And the amount that that F3 increases has everything to do with the ratio between the seat area and the sensing area. So in this case, some pretty easy numbers here in that we have a 1 millimeter squared poppet area and a 100 millimeter squared diaphragm area. The ratio is 1 to 100. Our SPE is 1%. And most often these are listed in the documentation or catalogs and things like that as far as percentages or ratios of SPE. So what that means is that if our inlet pressure decreases by 1,000 psi, the outlet pressure will increase by 10 psi, and this maintains the balance inside of that regulator. So let's look at it from a practical sense. Supply pressure effect for this regulator is 1%. So if we have a depleting cylinder, goes down by 1,000 psi, we know that it's a 1% SPE because we found it in the catalog or is in the technical documentation, whatever it is. We know that that 1,000 psi decrease is going to yield a 10 psi increase, so 1% of that 1,000 psi. And for some systems, this might be okay, right? So you may be able to handle that 10 psi increase. For other systems where the downstream instruments or the test or the process is more sensitive than that, we may need to get away from SPE or minimize it, right? And the most common way to do that is actually with 2 regulators in series. And the way that this will work is that you get supply pressure effect. There's no getting away from it. But the second stage only sees the output from the first stage. So what this means is that if we have starting points of 3,600 psi, 500 psi, and 50 psi, right? So first stage outlet is 500, second stage outlet is 50, just the same as our previous example. So if we lose, in this case, 2,000 psi from the gas cylinders, our first stage will rise by 20 psi, right? 1% of 2,000. Now, the second stage regulator has no idea that it's connected to a cylinder that has just lost 20 psi. All that second stage regulator sees is, oh, inlet pressure went up by 20 psi. So I have to readjust to maintain that balance. Now, the second stage output is reacting only to that 20 psi increase. So it actually goes down by 0.2 psi or 1% of 20 psi. So for all intents and purposes, SPE is effectively eliminated, right? So it's a really, really slight drop that won't affect many processes or tests, right? Only the most sensitive would require a third stage. So two-stage regulators can be set up in a couple different ways. For larger systems, you might have something on the left here where you have a spring-loaded high-pressure regulator up front, and then a really sensitive dome-loaded regulator second, and you still get that SPE benefit. Or for more compact applications, there are two-stage regulators. They work exactly like what we just talked about in that they have that in-series operation, and they minimize SPE. So again, when you select flow requirements, the temptation can be, well, if I need a certain size regulator, let's just get the next bigger one, right? Because that'll give us some extra runway if we need more flow. But what you will see is that ratio of the seat area to the sensing area could be thrown off, and you might get higher than expected SPE, right? So it's always best, if you can, use the flow curves to understand how that regulator is going to react. Choose the smallest regulator that can carry the flow you need to minimize SPE. And if you really have to eliminate or minimize SPE, go with a two-stage system, and you'll be able to get away from it pretty easily. So we've just gone through the hard stuff, right? So 2, 3, and 4, inlet pressure, outlet pressure, flow. Now we talk a little bit about compatibility and some of the system functionality before wrapping up. So when we talk about compatibility, it's the same as you would for any other component, right? Make sure the soft goods are chemically compatible. Make sure your body material is compatible. You do want to pay attention to the dynamic versus static seals in a regulator, because regulators are always moving. You want to make sure that the dynamic regulators, or the dynamic seals, so seats and O-rings on poppets or pistons, whatever, don't get any swelling or anything that could impede the movement of those products. So one of the things we do have to consider, however, with regulators is temperatures, specifically related to the Joule-Thomson effect. So Joule-Thomson is a physical phenomenon. It's not generated by regulators, but it is the change in temperature when a gas is allowed to expand, right? So typically what we see this in regulators is that we're going from a high pressure inlet to a low pressure outlet. The gas can expand and most often drops temperature. So for natural gas, it's about a 1 degree C temperature drop for every 2 bar in pressure drop. So for imperial units, it's about 2 degrees F for every 30 psi of pressure drop. So it could be significant. One way to combat that is you can either heat the gas, right? Or you can use 2 stages. So just spread the pressure drop out over 2 stages, right? So once we've figured out compatibility, now we've got to focus on functionality. And so the system functionality has everything to do with how the operator interacts with this regulator. And the biggest choice we have is venting. And there's really 2 choices for venting: self-venting, captured vent. And they're really driven by the media type, the application, any sort of safety regulations. And they're 2 separate choices. So I want to run through those before we wrap up here. The first one is self-venting. So self-venting is a feature of regulators when selected that allows you to easily change the set point of a regulator without having to vent the downstream pressure manually, right? So on the left, you have a non-self-venting regulator. So this outlet pressure, if we were to change from a 100 psi set point turn the handle counterclockwise, trying to get to a 50 psi set point. This outlet pressure, if it's, let's say it's isolated here somewhere, there's a downstream shutoff closed, that pressure has nowhere to go. So it would need to be manually vented in order to allow that set point to change. Whereas the self-vent regulator has actually this small seal at the top of the poppet, which interacts with the diaphragm, and there's a hole in the middle of the diaphragm or sensing element, it could be a piston, that when there's excess outlet pressure, so if you take the handle, turn it counterclockwise, you let that spring relax, so F1 goes down, F3 takes over, pushes this diaphragm off this seal, and that excess pressure can escape. And so that's really where the self-venting is best used when set points change a lot, right? So if you're constantly going up and down and up and down, self-venting can make that operation much easier. Now, that gas has to go somewhere, right? And so we also have, and many folks do, some version of captured versus non-captured venting. And as the name implies, a non-captured vent just allows that media to escape to atmosphere. So it does vent under the handle, so operators aren't getting bombarded with gas. But for inert gases in well-ventilated areas, this can be a great, simple option for those situations. Now, where you have a more hazardous gas or an enclosed space or anywhere that operator safety is paramount, you can opt for a captured vent version. So what we do there is we seal up the stem here and we include a threaded port. So that allows folks to put in a fitting or whatever else to connect in to the regulator. Should gas escape through the sensing mechanism, then it can be directed to a vent line, a flare header. It can be, even just pushed out the roof of a shed or whatever, but just pipe it away safely. So again, those are two separate choices that you can make: self-venting or captured vent. So then finally, we've got to connect this thing, right? So we need to know what the end connections are, what the porting method is, how these things are mounted. And in some cases, the gauges can be very important, right? So what orientation is the gauge going to be in? Where will it sit? So in some of the more sensitive regulators, will it sit underneath or in front of the sensing area? Those are all things to be considered. So with that, we've made it through the selection process. And in doing these, I've created a kind of a cheat sheet, right, on what's required, what's kind of helpful, and then what are the things that are just nice to have when selecting a regulator. So the required stuff you need to know in order to execute these steps properly. You need to know what the inlet pressure is. You've got to know what your outlet pressure is. You have to have a flow in mind, or at least a range, right? Maybe we don't know exactly what it is, but it's in this range. And then clearly you need to know what you're flowing. Is it a gas? Is it a liquid? Is it hazardous? What is that, right? And so, feel free to follow these steps and use these guidelines when selecting a regulator. So I will absolutely hang around for questions. So don't feel like you have to get them in now or ask later if you want. I'm happy to hang around. I do want to do a bit of a review of what we talked about. So there are two types of pressure regulators, right? Pressure reducing and back pressure. Those regulators are driven by three elements: the control, loading, and sensing elements. So those really drive regulator behavior. Next is you want to make sure you choose the max inlet and control ranges as close to what you expect to use them for as possible. That's going to give you the best performance, most accurate, lowest droop. If you can, use flow curves to size those regulators. And if not, you can rely on the calculations or a flow curve generator in order to do that, understanding that a straight calculation won't give you any information around droop, right? But it does give you the right size of pressure regulator. And then in terms of self-venting versus captured vents, those are really should be considered on what your application is and what kind of safety implications would releasing that gas imply. So those are always important things to think about when you're thinking about system functionality. So with that kind of wraps us up here. What I will say is, and Gary, I don't know how you want to do questions, but there are a few in the chat. I'm happy to address those here, or if Gary, you guys wanted to write back the answers, I'm happy either way.
Yeah, John, thank you. That was a great presentation. Great job. Hopefully everyone picked up a couple things here. We have a question or two that I kind of just want to run through at the close here.
Yep.
I'll kind of start backwards. This one's related to the venting. So the question is, self or captured venting, it's phrased here, is it usually incorporated in single stage as well or only two stage? So I think the way that we saw it in the presentation, John, that was single stage regulation when you had the cutaways showing the venting options.
Yep, correct.
So I guess maybe the way the question should be read is it incorporated in dual stage as well?
Yep. Yeah, you can have self or captured vents in both single and dual stage regulators. Yep.
Yeah. So everything we saw there, guys, in the cutaways was a single stage regulator to show the venting options, but they can be incorporated in a two stage as well.
Correct.
And then this is a pretty good question here, an interesting one. The venting options, can that be incorporated, John, in any way for relief, to substitute a relief device?
Yeah, so it's a question we get quite often, and the mechanism by which the self vent works is really similar to a back pressure regulator or a relief valve, right? So it works on excess pressure, but the flow area is very small, and so the relief capacity is tiny. It's really made to relieve the excess pressure from changing set points, not a system overpressure. So the flow capacity is not there, and really the sensitivity isn't what you would require from a relief device. So while they function very similarly, we never recommend to substitute a self vent for a dedicated relief device.
Yep. That's good. And then circling back to a different one that I kind of hit on and tried to answer a little bit through the chat is, the question was a preference between or differentiate between a differential pressure versus a pressure reducing to ultimately get a better precision out of the regulator.
Yep. Yeah. So
go ahead.
So differential pressure regulators allow users to reference a point in the system. So a good example of this might be, and I don't know what industries everybody's in, but if you think about a dry gas seal on a big piece of rotating equipment, right? Very often that seal pressure needs to fluctuate with whatever's happening inside that piece of equipment. So one of the ways to do that is to use a differential pressure regulator. So what you do is you sense the pressure wherever you want to reference it. That comes back to the regulator and goes into the dome chamber. Now, unlike a typical dome-loaded regulator, differential pressure regulators also have a spring. So the set point becomes whatever's in the dome, so whatever you've referenced, plus any additional pressure you've dialed in with that spring. And then as the system pressure changes, right, it goes up and down, the set point will also change along with it. And so it's a different type of pressure reducing regulator that's enabled to reference a portion of the system or a different system anywhere that you want to reference, really.
Yeah, right. That's kind of how I explained it. There is a different category or style of regulator, and there's various options and features that will help drive better precision out of either style.
Yep.
Okay, good. If anybody else wanted to type in any other question, I didn't see any more populate as we were kind of answering those. If there was anything kind of surface level, high level that we could kind of hit on or answer, not diving down into the weeds too far here. You could unmute and answer it real quick, but we don't see anything else coming in here. Here we got a question. Customer uses a regulator for vaporizing and they get Joule-Thomson effect, and we need to change the regulator regularly. This is a heated line. Should they be looking at potentially a differential regulator?
So if it's Joule-Thomson related, a good solution may be also looking at 2 stages.
Yeah.
So especially if the line's already heated, gases pick up energy really fast. And so even just spreading that pressure drop over 2 units, it can be really helpful to combating Joule-Thomson, because the reality is you can't get away from Joule-Thomson. It's physics, right? If the gas expands, it's going to cool down. But what we can control is when that happens. And so splitting it into 2 stages, we've even seen some folks have success with, depending on where you are in the world. Obviously, we don't, so I live in Cleveland, and you all in the kind of in the neighboring area there. Our winters get cold, so we can't always rely on hot weather. But if you're somewhere near the equator that has pretty consistent temperatures, we've seen folks that have 2 regulators separated by just like a coil of tubing, right? And it just soaks up energy from the atmosphere. So really simple things like that can help as well. But those are the kinds of things that if you do run into them, don't ever hesitate to reach out to Swagelok, the local folks certainly, and the field engineering team. That we can always help to talk through a lot of those challenges.
Yeah, those large drops in pressures off of a source getting down to 100 psi or so, 2 cuts is a way to do that, and it usually solves the problem.
Yep. Yeah, and it looks like there's another question about Joule-Thomson effect, the reverse Joule-Thomson, and especially for hydrogen. Yeah, so there's 3 gases, right, that actually heat up. It's hydrogen, helium, and neon. Neon we don't see very much of, obviously, but hydrogen and helium certainly, right? Now the one benefit of that is that the coefficient, the JT coefficient for those gases at the temperatures and pressures we usually encounter them is actually pretty low, so they heat up slightly. Now, if you have massive pressure drops, obviously you'll see big changes. But yeah, similar suggestion, but you would just go the cooling route versus heating if you needed to.
And then John, popping in real quick on mass flow controllers. I don't know how much experience you have on those as well, but I'm a little bit familiar with it too. They do require a constant back pressure across the mass flow controllers. Do you have any insight as to why that is?
I don't spend a ton of time with MFCs, at least in the regulator context, right? But
right.
What we actually have seen is for some of those units that require a constant differential pressure, you can actually use a differential regulator, right? So your reference point becomes the point just downstream of the MFC. That gets fed back to the regulator, and then you can add in whatever you want your differential to be using the spring. And then as anything changes, the regulator will work to maintain that DP. And so that helps the MFC drive the right flow or control the right flow.
Yeah,
so we
one
have
regulator
successful there. Yep.
Yeah, one regulator, regardless of your inlet pressure fluctuations, it'll maintain that constant differential.
Correct.
Yep. Okay, well, those are some good questions, guys. No one else has anything at this time. I think that's about it. So yeah, we're a little bit past time here, so we'll kind of wrap up and let everyone get on with the rest of their days here. But we do appreciate everyone popping in here and being engaged, and hopefully everyone can take a couple pieces of information away with them that they didn't know coming into this. And like John has said, we're here locally here in Pittsburgh, myself and the rest of the team here at Swagelok Pittsburgh, to help you guys with any of these concerns. And you can see a lot of information goes into selecting the right regulator for your application to make sure it performs correctly and accurately and lasts a long time. So we're here to support you. We have John on board as well. As you can see, he's a subject matter expert. So we got a lot of great resources to help you guys get what you need and make sure your systems are functioning properly. This recording we have recorded this, so the recording should be made available to anybody that wants to see it again here or share with other people. So we'll make that available through a couple different channels, hopefully. And outside of that, thanks everyone for their participation. John, thank you. It was a great presentation. Always good hearing the insight on the regulators. So,
Of course, happy to do it.
We'll kind of wrap up, and thanks again, everyone. Have a good rest of your day.
Thanks, guys. Thank you.